square plus 2 times of the gradient of u square plus the integral of u power 4 dx, okay, u power 4 dx plus d by dt of integral of the gradient of u square u power 4 upon 2 plus plus norm of u square actually, okay, u square. This is what that you can do. Norm of u square dx. Or if I wish, I can also rewrite this as this, that d by dt, by the way, d by dt of there is a time derivative, so there must be a time derivative. Okay, so if you're going to put these terms together, by the way, this I can write this as the gradient of u square plus this term, which is going to be the norm of u square plus the integral of this u power 4 upon 2 dx. Okay, this is what that you're going to get. And this is less than or equal to, here you have norm of u square plus the constant c. So let's call this equation number 3 actually. Okay, inequality number 3. This is what it is. Now, in order to have the H2 estimates of the solution actually, let's do one more step. Let's do one more step. Take the same equation, ut Laplace u minus u cube. Okay. Let's first differentiate with respect to t. So when you're going to differentiate this with respect to t, what are you going to get? So when you're going to differentiate this with respect to t, this will become ut t. This will become gradient ut, this will become ut minus, this will become 3u square ut. Okay. This is what it is going to be. And now integrate, okay, integrate this equation, multiply this equation by ut and then integrate with respect to space variable. In other words, take the inner product of on both sides of this equation by ut. So you're going to get the gradient ut. This will help us to basically have an estimate on H2 norm. Plus ut minus 3u square ut and ut. Okay. For this, I can pull out, for example, one time derivative. So I need to put a penalty of 1/2, and you're going to have ut. So I can say this is going to be the norm of ut square. This will become what? The gradient minus gradient ut. So this is going to be minus norm of gradient ut square. So this term will become the gradient of ut square. So let's put it on this side. So this will be positive term. And this term, which is a negative term, let's take this on this side, is going to become what? So this is going to become 3. So if you write it explicitly, 3u square ut square dx. Okay? And all this is equal to this term, which is norm of ut square. Okay? Which is norm of ut square. So let's call this as the equation number 4. So what I'm going to do now, I'm going to multiply this equation by 1/2, okay, and add it into this inequality. So when you're going to multiply this equation by 1/2, this will become 1/4, 1/2, this will become 3/2, this will become 1/2, okay? Okay, I'm directly writing the result actually. Okay, so take this equation and add it into the inequality. And by adding it to the inequality, what I mean that, okay, put these derivative terms together and rest of the terms together. So when you're gonna do this, you're gonna get an inequality of this kind actually. So dE by dt plus E of t less than or equal to some constant C actually. Okay. Where the E of t, so you got your required inequality, where the E of t is this long expression, which is norm of u square plus the gradient of u square plus 3u square ut square dx, okay, and so norm of u square plus gradient of u square plus 1/2 u power 4 dx, integral of u power 4 dx, plus 1/4 plus 1/4 of norm of ut square actually. Okay, so if you take E of t to be this and add this into this inequality, you're gonna get basically this differential inequality. So I'm not doing these elementary calculations, so do it for yourself. So you got the differential inequality. Now once you have the differential inequality for E, okay, it's not difficult to add this differential inequality. So this is really going to be easy. Just multiply on both sides by the integrating factor, okay, and evaluate E of t. So when you're going to solve this inequality, so it's a linear inequality actually, really easy to solve. When you're going to solve this inequality, the E of t is going to be less than or equal to E of 0, some constant, E of negative d plus a constant C1 actually, okay, plus a constant C1, where E of 0 is what? The E of 0 is a norm of u0 square plus the gradient of u0 square plus 1/2 of the u0 power 4 dx plus 1/4 of, now u0, so okay, I mean it doesn't make sense to calculate the time derivative of u0 actually. So what we can say, I know that ut is Laplace u plus u minus u cube, so I can say that this this last term will become like this actually. So it's going to be Laplace u0 plus u0 minus u0 cube actually. Okay, so this is really is the E of 0. Okay. Now, from where these initial conditions u0s are always being chosen, they are being chosen from what do you call this H2 intersection H1, so from this space H actually. Okay. Then what we can do, then you have always estimates for what do you call, you always have estimates for the L2 norm and H1 norm of the initial conditions. So in other words, by Sobolev embedding theorem by Sobolev embedding theorem for initial data varying in a bounded set of H. Okay, so if you choose these U naught such that they vary in a bounded set, varying in a bounded set, okay, in H, we can find, it's not difficult to find a positive constant, say m, such that E of 0 can be estimated by this number m, where obviously this number m depends on the bounded set of the initial condition, in which the initial conditions are varying actually. And the Sobolev embedding theorem is going to help actually. If you have this, okay, if you have this, your inequality will become what? Okay, so or this inequality, I can see that will become E of t is estimated by a constant depending on the bounded set E of minus t plus constant c1. Okay. By the way, this constant c1 does not depend on the initial data. This is a constant that depends on the measure of the domain actually, the measure of the domain. You remember the constant that we had in the first inequality. Okay, so this is the same constant, or a constant depending on that constant actually. Okay, so this is what that you're going to get. Now I want all of this constant to be less than or equal to this constant, to some fixed constant depending on the bounded set of the initial condition. So in other words, I want this constant to be less than or equal to some constants. Let's call this constant, I don't know. Let's call this constant C actually. How you can find this constant? It's not difficult actually. So if I choose, say, so if we take say what? So if I take an instant Tm, in other words, from this inequality, if I try to deduce a value of t, so that value of t is going to depend on the log of m and c1. So if I take say Tm to be the log of m and c1, okay, then for all t bigger than or equal to Tm, this constant E of t is going to be less than or equal to what? So I can substitute this here, and what you can see that everything will cancel out and you're going to get E of t less than or equal to the 2 times of the constant c1. Okay? It depends on the 2 times of the constant c1. So in other words, we got what we require actually. So one of the key ingredients that we require, that our energy should stay in a ball of the radius, what do you call, of the radius, which is a constant, which may depend on really, what do you call, the bounded set of the initial conditions actually. Okay, so this is what that we wanted. Now, how we can have, so from this we would like to have, and by the way, you have to keep in view that E of t is this number. Okay, so E of t is this quantity. So if the E of t is this quantity, then I would like to have an estimate on what do you call the H2 norm of U. So by using the regularity result, okay, so for elliptic boundary problem, okay, so we know this inequality that the H2 norm of U square can be estimated by C times of the Laplace U, the norm of Laplace U of T actually, square. Okay, so this is a well-known inequality. And if I say, write that, okay, Laplace U of T is really is ut minus U plus U cube, okay, is going to be ut minus U cube. I can write it in this manner, that this would be, I can say that this is equal to the constant of say ut minus U plus U cube, and it's a square. Then applying the suitable inequality, the triangle inequality, or the inequality that, okay, A plus B plus C square is less than or equal to 2 times of A square plus B square plus C square. Okay, 2A square plus 2B square plus 2C square. Applying that kind of inequality, what you can get, I can get a constant, say C2, for which this is less than or equal to norm of ut square plus norm of U square plus norm of U cube actually. Okay? And since this energy which contains these terms is less than or equal to this constant, so you're going to say this entire thing is less than or equal to a constant, I don't know, let's call this constant as C3. Okay? Since E of t, which is this expression, is less than or equal to some constant C1, so therefore this thing is going to be less than or equal to some constant C3, which depends on C1 actually, okay, which depends on C1 and this C2. So what is the net conclusion? The net conclusion is what we proved, that the H2 norm of the solution of our nonlinear evolution equation is star, okay, is less than or equal to square root of C3. In other words, is less than or equal to C3. By the way, this is true for all t bigger than or equal to Tm, so obviously this is also going to be true for all bigger than or equal to some instant Tm, or some fixed instant actually. So in other words, after some instant, the H2 norm of the solutions will enter into a ball of the radius C3 and they will stay there. Okay, so these norms, H2 norms of the solution are going to stay there forever actually. So what does it mean? It means you found an absorbing set for the solutions U of t actually in H2. So you found the absorbing set, and once you have the absorbing set which absorbs the trajectories of the solution, okay, in H2 norm, you have the existence of the global attractor from the previous theorem, because if this is true, then the condition 1 of the sufficient condition that we proved is true, and if this is true, you have the global attractor actually. Hence this completes the proof of the result about the existence of the global attractor for the reaction diffusion equation. So I know it's a lot of work. I have left a lot of things for you to work on. So what you have to do now is to make sense of this stuff first in in the book. There is another example whose global attractor is being studied. It's a nonlinear wave equation. Okay, it's a nonlinear wave equation. So I would suggest actually that you should study that example as well, 6.4.2. And one of the assignment of you and task for you is going to be to study the existence of the global attractor for the equations that has been assigned to you actually. So I hope this is making a little bit of sense to you, and thank you very much.